So what we've previously done is create this class called Scalar, right? Which basically allows us to create a custom variable, assign it a value, and now we've defined the addition and multiplication operations on this scalar class, right? So if you can say scalar is 2, and you can then say b is a 1, and you can add a and b, for example. Right? And this is our first part in setting up our Autograd system. Now, what's the next step? Well, if you want to differentiate backwards, we want to know or at least visualize the computational graph. So let's modify this now so that we store the parents or basically the values that result in this particular scalar being created if there are any. So we're going to say previous, right, is empty to start with, or it's going to be passed in. We're going to say self.previous. It's a set, right, of previous, right? And what we're going to do is say, so how does that work? So if you say add, you basically, when you say add, and you call add on say A, what you're doing, you're saying, well, A is self now, and other is what's passed in, right? It's B. So when you create this new scalar, which is now what is going to be C, you can also pass in self and other. Because what are we saying? We're saying, well, actually out or C, in this case, if it's C is A plus B, is dependent or created from self and other by adding them. So I'm going to say this, and what will happen? It will go here, and in previous, it will store those two values or references to those two. So now it has a history of what resulted in that scalar object being created, if there is any. If there isn't any, then nothing is passed in, and so previous, there isn't a previous, right? So we do the exact same thing with the product as well. We're going to say, let's pass in self and other, right? And so for the multiplication as well, it's now going to store the history. So if I say now print a dot previous, nothing, right? It doesn't have a previous. On the other hand, if I say c dot previous, a and b, right? And because we have defined the print using the repr function, it does print the value of a and b as well. Similarly, if you say e dot previous, it says c and d, right? Correct. So now it has a history, or it records the history of how it was created. Let's add one more piece to this. Let's also give it the information of the operation. So we're saying self.operation, and we're defining it to be empty. There's nothing there. However, now in this case, it's multiplication. So we're going to say multiplication. Or in this case, this was addition. And in this case, we're going to say it's multiplication. So now it also knows that it was created from these two, but it was created by multiplication or addition. And so what we can do next then is visualize this, right? And visualizing it then allows us, when we implement the backward pass now next, to kind of understand how this was working, right? So how do we do that? What we need to do first is kind of accumulate or find the nodes in the tree. So we're going to first, what I'm going to call generating the graph, right? We're going to do that first. And then we'll visualize the graph. So how are we going to generate the graph? Well, so the graph has nodes, and we're going to make that an empty set, and it has edges, right? Where the nodes are the actual, in our case, the way we're visualizing it, are the actual variables, and the edges are the connections. So what are we going to do? We're going to create a function called generate graph, right? And what's going to be passed in? A node is going to be passed. What is the graph going to do? It's going to, well, first say nodes dot add node, right? And because it's a set, it won't duplicate, right? Okay. And now what do we want to do? We want to say for, we're going to iterate over. So I'm going to say for prev in, and I in self.previous. So it's going to iterate over the previous. And for each of those are now where what resulted in the operation, right? So that's the previous step of the graph. What is it going to do? It's going to say, well, first, those are the edges, right? That's where the connections are coming from. So I'm going to say edges dot add. And now what is the edge I'm adding? I'm adding which previous it's come from. So this is a tuple, and it's going to be what previous node it's come from, or the connection is coming from, and the current node, right? So we've got the edge, which is basically the connection. And so for each previous, the connection is coming from the previous to this node. And once we have done that, what do you want to do? Well, you want to know the connectivity before that. How do we do that? Well, we go generate graph on the previous. Right? So what will it do? If you pass C into this, if we go and take C, it's going to add C to this graph. Then it's going to go and say, okay, for previous and self dot previous, what are the edges? We know C, the parents were A and B, and it was addition. So it's going to say A, it's going to add the edge A to C. It's going to go and then generate the graph for A. It's going to find that A, it's going to add that to the list of nodes. It's going to find that it has no previous. So it's going to skip this step. There's no child, right? Or no previous. On the other hand, and it's going to come back now and say, what's the next, previous to C? We've done A, well, B. Do the same thing, and B is going to get added. Now, if there was something before A, then for A, it would have its previous nodes, and it would run the graph on that. So recursively, it's going to call this generate graph and generate the entire connection history. So if I call generate graph, and I generate that on C, right? And then I say, let's print the nodes, right? Let's edges, and let's see what we get. So it says self is not defined, and that is because it is node dot, it's not self. And so you get C, then A, and then B, and the edges are A to C and B to C. Now we know that D is obtained from C, right? C times D. Well, no, E is obtained from C times D. What if we do this for E? Let's rerun that. Now you have A, B, C, D, E, and the edges are D to E, A to C, C to E, and B to C, right? And you see why it's doing that, right? Why it's doing D to E and A to C in this order as well, because it's going to take E and then go to D, and then it's going to keep going back from there, right? Okay. So let's now visualize this, right? So we'll use graphviz, right? I'm going to import diagram from graphviz, right? So you can install this. It's very easy to set up. And then, and I can add a note on that, how to set up graphics, right? But we have done that previously on this channel as well. And so what am I passing into GraphViz? I'm passing in the nodes and the edges. And it's a very simple kind of visualization. So I'm going to say graph is digraph, right? And the format is SVG. And the graph is from left to right. So graph So it tells you that the graph is going from left to right. I didn't close this. It's my bad. And what are we going to do? Well, we're just going to loop over the nodes, right? We've already created that here. And we're going to say graph dot node, which adds a node, right? And what do we want to give it? We want to give it an ID. So we're going to say the label is the ID, node dot label. And then what is it going to visualize, or what's going to be printed? Well, we are going to print, and this is the way to do it. You say label, and we're going to say, I want to print percentage S, and all I'm printing for now is right. So now I'm just printing the label, right? I don't want to print anything else. And the shape of this is record, which will print a square. And then I want the edges as well. So edges, and I'm just going to print the edge. So I'm going to say graph dot edge, and it's edge 0 and dot label. So the edges and yeah, the edge, right? Edge 1 dot label. Now this is to a certain extent a bit hard coded for the kind of problem we want to set up. For more complex graphs, it might not work all that well, but I think this will do for us. So let's run that. And then I need to visualize this. Graph. And now I'm going to say graph 1 is visualize graph. And I'm going to pass it nodes. And technically, nodes and edges are there, but let's just put in. Let's run that. So graph 1, that. And let's run that. And it's running, it's generating the graph, and we've got that. So we've got A, B going to C, C and D going to E. Now, what are we missing? We don't have the operation. So let's add one more thing here. Let's just, before this, add another else. And let's say node dot operation. Right? So I believe I did store it. So if there is an operation, it will. Let's rerun that. And not enough arguments for string. Did I goof up on that one? Okay, it's my bad. This should be it. And now we're good. Okay, so node dot operation, I have to reset this. Let's rerun this so that the operation is stored. And it isn't. It is storing the sum here, it's storing the product here. Self. Okay, I haven't stored this here. Let's find it. Let's rerun this. And so now we see A and B, it's a plus, and you get C. You see D and C, it's a multiplication, and you get it. So now we've been able to visualize the computational graph, right? What I had forgotten here was to actually take the value that's been passed in for the operation and set the self with that. Good. So we can now visualize this simple computational graph. We can see what's happening. What's the next step? That's the most important and fun part. We're now going to implement the backpropagation or the differentiation part, right? Okay. So let's do that next.